Hello. Okay. So is this the right presentation? Yeah. Okay. Doesn't matter. Cloud computing. Okay. Oh yeah. Oh yeah. Thank you. Let's start. Okay. So I'm Shen Wang. I have graduated as a PhD from the State University of New York at Binghamton. I'm trying to just present the paper here of the WebAssembly memory tagging paper for the cloud computing security workshop 2025, right? I cannot go to the Taiwan because I'm now in mainland China. I have returned to China. They won't allow me to get a visa to go to Taiwan. So I have to make this presentation first. Okay, let's get started. So today's topic I'm talking about is the WebAssembly memory tagging. So first, the web is important. We have front end, we have Electron apps, right? Nowadays we have progressive web apps, and if you look at my channel and look at all my everything I said, I would argue that web is becoming the progressive web apps are becoming more and more important. So the web is becoming very, very important. It's more important than native, in my opinion. It's not just in front end. You're also using it in back end, like Node.js, like all some weather virtual machines, and people are doing crazy things like putting WASM in the kernel or compile WASM to JavaScript to Lua, even running in many game engines or something like that. So the web is important. And usually when we write web, we use JavaScript, CSS, and HTML, right? But JavaScript is pretty slow if you try to do some very computational, comprehensive things. And now we have WASI preview 2, which is trying to even eliminate entire JavaScript. So now we have these things called WebAssembly now, right? The WebAssembly is a binary format that just can allow you to execute code that compiled from native language from C and C++ and Rust cross-platformly. And you get the WASM binary, it's gonna executing something like WASM virtual machine, which is like Java does, or running a real in the browser itself, like JavaScript does, right? However, when you compile C and C++ into the WebAssembly, and we know C and C++ are not memory safe, so if you have a memory safety issues in your C and C++, it's gonna still create. Those bugs won't just disappear, right? The sandboxing of WASM mitigates some risk, like you won't be able to just directly hurt the kernel, for example, or go outside the sandbox. But it can still create problems, and the everything old is new again. The binary security WebAssembly by Li Han and Kinder and many other security groups like them. They just demonstrated it's even possible to do like things like control flow violations. They can control the control flow of the WASM program, just like in native program, to do something like cross-strip side attack, which is that the problems if your C and C+ code is not memory safe, just putting the WASM it doesn't make it safe. Now you might say I'm just using Rust. Well, Rust, although it was improvement, but if you look at the CVE details, you can still find tons of security vulnerabilities with Rust, although they might be less than C and C++ because with better boundary. And we know C and C++ now is, particularly C++ is now trying to improve the language, but these problems just don't necessarily goes away. Plus, you won't necessarily just rewrite everything in Rust. Right? You have tons of code, existing code. You have your code engine with probably reading C++. You don't want to rewrite them. So that's why WebAssembly memory tagging, WebAssembly memory safety for the program is still very important. And WebAssembly has its own specific challenges here. Is that WebAssembly is supposed to run cross-platformly. It needs to be portable. When you try to be portable, you have to make your format to be simplicity and portability, right? So, like you cannot easily implement ASLAW, randomize your address space. You cannot have page protection. And even you do have that, what are you going to do with it? Because neither ALCLR or page protections like that kind of defense are going to fix your memory safety issues, right? If they could fix it, we won't have issues with talking about these memory safety issues in C and C++ or native code now. So it's just trying to introducing everything like ASLAW's page protection into web. First, it introduces complexity. How do we implement it? The pages tables are implemented by the hardware, but if you implement it with software, it's going to be massively expensive compared to implementing in hardware. So we think the solutions need to be simple, right? The memory access here, if we will try to improve the memory safety, it needs to be simple solutions, right? I happen to know one, which is simple, which is what I'm trying to say here is I've read the ARM memory tagging extensions, and the ARM memory tagging extension, like for example, they mentioned Kuaishou, a leading content platform, and they just detected 90% of bugs before release, and 3 times the scatter speed and native RAM decrease by 60, which is all the good stuff they had, right? Which is the successful story by newsroom by ARM. And now even in AMD is all proposing proposing memory tagging into x86 too. So which means it's becoming something like industry standard because it's proven to be very secure and be a good solution. Although it cannot guarantee everything, but it's much better than what we have today, which is nothing. Okay, so first we need to explain the memory tagging mechanism. Like I said, it's just from a generic perspective. So what memory tagging does is that it just try to divide the entire your memory address space into divides every 16 bytes into a unit, which is called granule here, right? Which is by the ARM MT. They call it granule. The granule. Let's assume we're using malloc to allocate 35 bytes. The malloc function would actually give you allocate 48 bytes. And with these 48 bytes, probably also with some header, but it's just the actual memory it allocates to you are 48. It tries to align to 16, with the 16 aligned, and this entire 48 bytes of address are going to be giving a color. So when we use a malloc, the malloc will return the color here of the memory here. So when we try to access a pointer, it will check whether the pointer of the tag of the pointer plus the pointer arithmetic is going to be the same as the pointer, the tag of the color of the memory. If you have a incorrect pointer, it won't work, right? It will crash the program, which is basically how it works. Okay, I'm not going to explain all the details. You can just go MTE. But here, because I know this mechanism, I think introducing memory tagging to the WebAssembly memory tagging would be a good approach. So first, since the memory model is linear, basically big array, WebAssembly's memory model is big array, we can actually implement the memory tag very easily because we can just put a tag with another big array and the tag is not accessible by a user. Will be done, right? We won't be able to add tags for every page, for example. You won't do that. You won't hide the tag somewhere. You don't need to do that. And we choose to align the behavior of WebAssembly memory tagging with MMT, which is that the granule needs to be the same. All the text doesn't need to be the same, but the granule is still 16, which is that we still divide the entire memory into 16 bytes. Because we want to say if you're running on hardware with ARMMT, we want to directly using the ARMMT to implement this. Translate the address, memory address in the WebAssembly sandbox into the real tag in your hardware. And we do that. We've done that by modifying LVM and an LVM-based WebAssembly virtual machine. The fastest one I've known and proven by many benchmarks is called WAVM. Although the virtual machine is no longer maintained by the author, it's basically maintained by me. So we modify the WAVM and LVM base to support this memory tagging as a demo. So other virtual machines, even the browser itself, can just use it as a demo to implement it. We just use it as a demo because they both use LVM, which is easy for us to implement it because they are both LVM. Plus, the performance of WAVM is very good, often at the top of every other implementation. Using that as a base benchmark would be efficient, right? Not efficient, be persuasive, right? If we choose a slow benchmark, a slow virtual machine, it's probably improvement. Maybe it has improvement, but you can say maybe it's because the virtual machine itself isn't implemented very fast. So we're going to use we need to use the most efficient one. And the tag of the WebAssembly memory tagging is going to store in a shadow memory, which is not in the export directly by the users. Plus, we're going to put a non-zero tag to the WebAssembly memory address with a non-zero tag. The problem with WebAssembly is that if you try to access, for example, the new pointer, you will try to dereference new pointer. Since it has no page tables, it will still execute it. You just like you're doing nothing, which is not something you will see in the native code, right? If you try to derive your non pointer, although you might have compiler can optimize no pointer away, causing undefined behavior. But here, even you try to actually dereference it, access that memory, since the memory address in the sandbox is not real memory address, you won't get a crash. But now if we give it a tag, it will crash the program. So how many bits to tag? Well, the VM is free to decide how many bits to tag. So in our software implementation, we choose 8 bits for 64-bit WASM and 4 bits for 32-bit WASM. For 32-bit WASM, we just put the top 4 bits of the pointer for the tag. Then the detection rate will be 1 minus 2 to the minus 4, which is 93.75%, which is that if you have 16 colors, so you're going to have this, you just do a simple math here, just 2 to the tags, right? 2 to the n. My 1 minus 2 to the n, which is my 1 minus 2 to the minus n, okay, which is the detection rate, the collision rate, right? But since 32-bit memory only has 4 gigabytes at most, you can access, it's going to reduce the usable memory to 256 megabytes. It might be an issue, but I don't think it's going to be a big issue because if we're back in Windows XP era, even the entire OS plus a program is only 248 megabytes, but it's still running very fast. Back in Windows XP era, that's entire kernel plus a program. Now with just a simple program, you can have that kind of much memory. So it shouldn't be a big issue for most programs. But when you do have, you need 64-bit memory, which is that you need 8-bit have tags. Then you won't have this reducible memory because the memory address is too big, and you're the detection rate will be 1 to the 2 to the minus 8 would be 99.61%, which is basically you can always detect the program. Plus, it will automatically translate WASM mem tag to ARMMT supported machines like my Google Pixel 9. So you will use the hardware implementation by tagging the top 46 to 49 bits like ARMMT does for 60 WASM. For 32-bit, just directly shifted the 4-bit tags to that bit, okay. So we have 4-bit tags when your machine do support ARMMT. Even in the future, if x86 support that, we can just directly use their tag. It doesn't necessarily be 4 bits. Maybe they use 8 bits here. But here you see the advantage here is that WebAssembly memory tagging is transparent to user, and you don't need to recompile a program, and it will work with if the machine supports it. So here is a table we added, which is the instruction we added into both LVM and the WAVM. Like this, I'm just tons of them. Basically, a lot of just very similar to ARMMT here, because we are trying to use the idea here. Like, let's assume that we have the memory tag, memtag load, which is it's gonna load the tag with a pointer. The pointer itself, for example, it will reserve the lower bits, but also add the tag in the upper bits here. Okay, and when we can store the tag, we can use the pointer to stack the tag. And this here what's the difference makes this different is that if using ARMMTE, it will tag only 60 bytes. But here our memory tag, it can tag any arbitrary of bytes. Okay, what it tries to do is that it tries to first right shift the tags you're having and then left shift 60 bytes. So you're going to ensure that it's going to truncate it to the actual address. So even you pass something like I'm tagging 31 bytes, you're going to end up tagging 16. Okay. So you won't just actually tag 31 bytes, but even 32 it will be 2, right? Like 2 grand now. Also you have the they here. They is basically store zeros in memory here. We also have a hint is that basically ensure that the tag it's basically for stack thing. Like, okay, I'm going to explain it later. So here we have a C++ code like hello or CPP. We compile with a clan. So we modify the clan to allow it to generate intrinsics, because this heap you probably need to manually use a tag in your C++ code. And then it will emit LVM IR, and LVM IR will just put in the WebAssembly backend. The LVM IR, when we pass the client with mem tag, the LVM, they have existing infrastructure will tag whether here you need this tag here, right? Okay. So then it will translate into WebAssembly our tags, and then we also need a modified what's the libc, that in the libc itself we tag we give the malloc and free calloc, realloc, some that kind of functions, tagging them, and then after that we're gonna modify the WAVM, which is also using the LVM, by emitting the instructions here to actually implement in the tag in the virtual machine itself and translating to the machine code. And it will end up with basically your code you can execute it here. Now here's what the hint is doing here. So we have a tag here. We have a buffer. It try to get a memory to get a tag, and then it will using the hint, which is the first object here. If it is hint 1, it's gonna add this pointer and add 1 to the tag, which is then we will ensure that the adjacent stack object they're gonna have different tags. So you won't have the first object to overflow the second one. Here, because we use the first tag plus a hint to do that. Although the hint, the virtual machine is free to ignore it. If it ignores it, it's just like a random. Okay. And it will store the tag. We can store the tag here. And after we go outside the stack, it will clean the tag back to what the origin is, which is clean up the tag. Now, what about heap tagging? The heap tagging is basically when we allocate the memory, just try to add, just directly after we get the memory we allocated in the malloc function, we call this built-in function. It's going to emit we just modify client for front end, right? The front end will give them a built-in, and it will translate into LVM IR, then translate to the WebAssembly tag. Now here we have the flag 1 here is that if for calloc is going to use the 1, so you don't need to do memset here. We can see them if it is not using the tag here, it will try to use memset. But here, the tag, the zeroing part will be dealt by the virtual machine itself. So it's gonna not be you won't have the memset here. So if it's just normal malloc, we don't need to zero it, right? Now what about the free part? When we free it, we will load the tag of the pointer and try to see the tag in the pointer whether the match is here. If it's not matching, we just print something out and just crash the program. You can choose not to print it if you care about the binary side. Okay. And after we do the match here, we will just untag the pointer, which is using untag. We will clean up the the tag here. So the address space will bring back to the original state, which is not tagged, which is for heap, just like what ARMMT does, right? So let's talk about the virtual machine part. We just talked about the implementation part of the compiler, right? Compiler part. Now we're talking about the virtual machine part. The virtual machine, we have two implementation, which is one is purely implemented by software. So if it's by software, we need a random text loop buffer. So this is in some shadow memory. This shadow memory has, when the program starts, it will have a buffer here. So the buffer, the size of the buffer will be different each time you run a program. And each time when you try to call, for example, you call memtag.random, it will just try to extract the the object, the color here in the buffer and put it back here. Now, when you go here, your curve pointer, you will move. If it's here, it's just like IO buffer, it will rewind, which is basically a loop buffer. It will keep extracting tags. And each time you run a program, the size of the buffer will be different. The content of the buffer will also be different, which is a randomized buffer. We're going to keep extract the pointer. So even if they can just guess one run, they cannot guess the second run while you run the program. It also avoids issues like what if you run out of entropies? I've seen the problems. I think there's probably a problem in the ARMMT case on the Google Pixel where they actually run out of the entropies in my benchmarks. So I'm not even using that for hardware implementation, but that's something else. Now, the problem with this software implementation is that we need performance, which is that it has a problem is that if you have something like doing a type hunting, you have an integer, you try to do type hunting, it crosses a boundary here. So if using release mode in my definition here, it will not detect it. It will just check exactly the address of the object it has. But if it's debugging mode, it will try to check the both of the address. Okay, which would be slower. But if that's what you want, you can get it. But mostly you just care about most of them because it's already powerful enough to detect most of them. I don't think just trying to detect everything is a good idea because security always has to be balanced with something else like usability or performance, right? Because what ends up with a security, we are using this machine. You cannot just tell me that I'm just prioritize security. I don't care about usability. That's a huge problem. Like Android by sideloading is a perfect example why that's wrong, right? Okay, let's talk about the hardware implementations of ARMMT and may expand to future x86 memory tagging because AMD just said they probably going to introduce memory tagging into the x86 64. But we're just talking about how the hardware implementation works. So here, when we tag pointers, we call this function. We will call the tag function, which is a loop function. We're going to clean up the entire tag here, but using the tag will be using the instructions to set them. And what I find quite interesting here is that LVM actually provides intrinsics, and we can just detect the ISA to say, oh, whether it is a constant or not. It is a constant, which is something like do text stack. We can just use the intrinsics, which is just directly become instructions, right? If it is not a constant, we just call functions, right? Call functions. Then you're going to ensure that you won't have the problem saying, hey, I'm just every tagging becomes a function call. That would be too expensive. Here we will have the problem. Okay. Okay, all the details, you can just go check my virtual machine implementation. It has all the details on how it implements. Okay, let's just check the evaluation. First, you might see, here's a problem here. You might see, oh, why the native is slower than even WASM? Well, I think the problem are two. Right? I think the major problem here is that Google is doing too much. On Google Pixel and the Android Bionic libc, Google is doing a lot on how to hardening the heap, right? So the hardening ends up being very, very expensive. So you can see that it's just it's extended to the point if you run in every application, it's going to run even slower than even probably like the slowest one with the ARM memtag here. Also, we know that ARMMT has this async and sync thing. I find that the sync thing is also very slow. It's even slower than something like, often slower than the debug. I don't know why. Than the software implementation. Even when it's, right. So the actual overhead is around 5.71% compared to native. We just check this one. We shouldn't just compare to native. We just compare to WASM itself. I'm just using native as example. We also have something like a Hawasan. It's also very, very slow compared to ARMMT. It's even slower than ASAN. You decide to call it Hawasan. It's actually slower than ASAN here, the native one, right? So from the WebAssembly perspective, you can see if we have memtag with ARMMT, it's actually pretty fast, right? If it's soft, it's gonna be slower, like 80% overhead, I think here, like 80%, I think. How much overhead? Let me check the paper. It's gonna be 72.38% of WASM for pure software implementation, but if you have ARMMTE, it's gonna the overhead is 18.5%. You can read in the abstract. If it is for WASM 64, it's 48.91% for WASM 64 for hardware implementation, but with ARMMT is reduced to 5.71% because for 64-bit, the memory address itself has a lot of overhead, even for baseline, compared to WASM 32. That's why it appears to be not right. It's a very small file, but the overhead I think is acceptable. You can just check the benchmark here in the paper and the abstract here. So what about the effectiveness? Here's what Microsoft has a table on showing the example on whether ASAN could detect all of them. We just use that example. We find that sometimes it just sometimes ASAN can detect something, and sometimes WASM can detect something. But if you're using WASM, not using WASM memtag, you will not detect anything, even a new pointer dereference. Because, like I said, the virtual machine doesn't understand the new address here. But with WASM memtag, it will detect new pointer dereference. Here's an example of showing how it works in real world. Like in dangling string view, like ASAN cannot just showing why WASM memtag is better because you can run on every hardware. It's portable and it can detect some bugs and what ASAN cannot detect, like this dangling string view problem. So we have a string view when you call something like replace index or replace even to string. We had a view here. We had a string view here, right? The string can just point to somewhere else now because now you reallocate the memory here. For the view, it still points to the original memory since ASAN doesn't have enough metadata, unlike the WASM memtag. It cannot detect this case. But the memtag can, or WASM memtag could, which proves the usefulness. And also we do find out, where's my slide? Okay. Also, we do find out why? the bug inside, for example, the WebAssembly libc. The WebAssembly libc, which is the libc for all the existing WebAssembly programs, right? And they have the new pointed references. We find it out, which is the bug has been 5 years, 5 years before we reported this bug, which means even it's just a simple bug in WebAssembly, nobody detects it. No, even just a new pointed reference, nobody knows it until we use mem tag to find it out, which proves that our WebAssembly mem tagging is super important and useful. Okay, that's all about this presentation, and thank you. If you have questions, you can just send me emails, and I appreciate everyone who help and supporting me on this research. And I hope stay tuned. Whatever.